In this video, I'm going to look at another past paper question. This one is about diffraction grating. So let me describe the question. In this question, we are given that there is a diffraction grating. So that's a piece of maybe glass or something with many very fine, closely spaced slits. And we're given that there is a light. There is a light. Maybe I'll draw it this way. Coming to this grating, and the frequency of this light is given as 6 times 10 to the power of 14 Hertz. Okay, so that's my diffraction grating, and we're given that on this grating, there are 4,000 lines per centimeter. Okay, and the question is, to find the angle. Between the third order diffraction maxima. Okay, right, so that's the question. Let's see how to do this. Now, first of all, let's just clarify what the question means. Okay, I've not actually heard this description of a diffraction maxima very much. In fact, probably not at all. In such a way, but I think we can guess what it means. It just means a diffraction peak, or diffraction fringe. Maxima, as in the highest, the place or direction that has the brightest lights coming out, because we know that diffraction grating gives fringes with very sharp directions, meaning that there are fringes going in along the center line. There's the first order fringe, second order fringe, going in very well defined, very narrow directions. Right, so that's our fringe. Okay, diffraction fringe. Third order, okay, just mean third order fringe. Now, angle between third order diffraction maxima. Okay, maxima is the plural of maximum. Okay, so that means we're talking about third order fringes. Right, okay, so it's not just one fringe that we're talking about. We're talking about more than one fringe. What do we mean more than one third order fringe? Okay, what that means is that there would be, okay, let's see, so that would be our central fringe. Okay, and that would be our maybe first order fringe. Okay, let me not draw that. So we might have first order fringe there, second order fringe, and then we might have a third order fringe there. Oh, I must well draw the whole lot. Okay, we have first order fringe here, second order fringe there, third order fringe there. Okay, so I have first order fringe there, first order fringe there, first order fringe there as well. It's symmetrical, right? So that's the zero order fringe. This first order, and I have a first order on both sides, second order on both sides, third order on both sides. So yeah, so actually there are two third order fringes, one up there and one down here. And this means that if we want the angle between them, we want this angle. Okay, that's the angle that we want. That's the angle that we want. So now let's think back at the formula that we normally learn for the diffraction grating. The formula for diffraction grating is d is equal to is d sine theta is equal to n lambda. So if we just recall this formula, right, if you just recall this formula, then the angle theta down here, the angle theta down here refers to the angle between the central fringe or the zero order fringe and the third order fringe. For example, if n is 3, right, n here is the order, so n is 3, is the 3 here. So the angle, the theta, would refer to this angle, not this one, right? This one, theta. So it means that it is half of the answer that we want. So obviously, if we can use this, well, maybe not obviously, but if we can use this formula to find theta, then we can multiply by 2 to get the answer. So can we use this? Let's see, right, okay, so as I was saying, 3 is the n. So let's check if we can, if we know the other values in this formula. Theta is what we want to find, so we don't know theta. D, do we know d and lambda? D is the distance between the slits. Now we are given that there are 4,000 lines per cm. Now 4,000 lines might mean slit, or it might mean the spacing between the slits. But in the other case, the distance between the lines would be the same as d. So with this information, we should be able to find d. Okay, so we can find that. We'll do that in moments. And lambda, do we know lambda? Okay, we're given the frequency. So we should be able to find lambda. So let's do these two first. We need to find lambda and find d before we can use this formula to find theta. So let's do that. Right, let's start from the d. So if there are 4,000 lines per centimeter, then d, spacing between the lines, will be 1 centimeter divided by the 4,000. So 1 cm divided by 4,000. So 1 cm divided by 4,000. Okay, we use our calculator to work this out. That will be 2.5 times 10 to the power of minus 6 meter. Okay, so we can find this. Right. Okay, then the next thing, to find lambda. To find lambda from the frequency, let's try that. We know that f lambda is equal to c, speed of light. So lambda is equal to c over frequency. C over frequency, and c, the speed of light, is 3 times 10 to the power of 8 divided by frequency, which is 6 times 10 to the power of 14. So once again, 0.5 times 10 to the power minus 6 of a meter. So now that we have both d and lambda, we are ready to find theta. So let's do it. Let's do that. So let me rearrange this. So sine theta is equal to n lambda over d. N lambda over d. And n is 3, lambda is 0.5 times 10 to the minus 6 divided by d, that's this one, okay, 2.5 times 10 to the minus 6 of a meter. And with our calculator, or we can do it by hand actually, we find 0.6. So now that we have sine theta equal to 0.6, this time we have to use the calculator. We'll give 36.87 degrees. And finally, to find the answer, we have to multiply by 2. So 2 theta is equal to 73.74 degrees. That's the answer.